the database is still fairly small. So you use them, then still use mainly thousands.
Why?
Why? Yeah. Because habits are difficult to kill.
Well, thank you very much to the organizers for giving me the opportunity to talk here. I'm going to talk about a possible way of doing a high throughput screening for 2D crystallization. So we are all familiar with many of the publications gathered in this table. This table basically tells you collects most of the publications dealing with most of the three-dimensional structures of membrane proteins that have been solved by 2D crystallography. If you look here in bold, these are basically structures that have been solved to high resolution, and the remaining ones are basically structures that have been solved to medium resolution. And many of the structures that are here in bold, they were either very abundant in their original membranes, and in fact, 4 out of these 8 are aquaporins, so a family of proteins that is very amenable for this kind of work. But really, one question is why haven't we been able to bring all these other membrane proteins to up here, and why haven't we been able to extend the number of structures on this table? I can tell you, for example, that I spent a lot of time on improving crystals of EMRE. We could get diffraction of untilted crystals down to 4 angstroms quite regularly. The minute we will start tilting, we will lose resolution. I know that Sierra and Subramanian has also tried to improve the resolution of OXL-T, and not successful. And of course, there have been lots of developments in microscopy and software, and the field is really moving on. But one of the obvious bottlenecks is getting 2D crystals that are large enough and diffract to high resolution. So this is basically the general strategy that one uses to obtain 2D crystals of recombinant proteins, not in situ 2D crystals, but basically of recombinant proteins expressed in whatever organism. And what we are going to do is we are going to express them. Imagine that this is your protein of interest here in gold. We are going to solubilize them, extract them from the membrane. We are going to then purify this golden protein. And then we are going to try to add back phospholipids, remove detergent, and hope that the protein will arrange itself into a two-dimensional lattice that, of course, resembles very much the original membrane to some extent. And then we are going to have to image these crystals to see how the entire process went. And sometimes we are going to have to come back here and try this protein, try different crystallization conditions. Sometimes we are going to have to go all the way here and perhaps select a different protein or select a different prep in order to improve these crystals. And the same for 3D crystallographers. They go through this flow chart here. They, of course, try to get three-dimensional crystals directly from here. But they do this process of expression, purification, solubilization, purification, and crystallization in a high throughput manner. And this has really impacted very much in X-ray crystallography of membrane proteins. So what we want to do is basically apply the same high throughput scheme to 2D crystallization. So for a high throughput screening, obviously what you need are milligram quantities of your purified membrane protein that should be stable in detergent. And something else that we wanted to test was what is the effect of sequence variation. So we needed access to homologs. In 3D crystallography of membrane proteins, often you identify a certain membrane protein you want to work on, and what you do is you identify genes that are homolog to that protein, and then you try to work with, in parallel, let's say about 10 genes, and you try to crystallize them, and sometimes, and you don't know why, a certain of those members is going to crystallize. So we needed to do this, we needed to have access to homologs and access to large quantities of membrane proteins. So what we did was we teamed up with the New York Consortium of Membrane Protein Structure, NICOMS, in New York, where basically they are expressing, purifying, and trying to crystallize in the order of 10,000 multi-span membrane proteins selected from about 92 prokaryotic genomes. And what they do is they have basically fermenters that can grow cells on a 96 well format. Everything is done in a 96 well format. They have a sonicator robot that will lyse the cells, and another robot that will basically do purification, his-tag, and so on and so forth. And then they have automated HPLC analysis, jet filtration, to determine what are the properties of those membrane proteins in detergents. And this is, for example, a given membrane protein run in all these different detergents and jet filtration. The same amount of protein has been loaded in the column. And you can see that this particular protein, for example, does not behave very well in DDM. There's a shoulder and the peak is very broad. But it behaves very well in DM or OG. And in this case, you will just take this membrane protein, this particular membrane protein, and you will only continue crystallization, but you will only produce it in large amounts for crystallization in one of these detergents in which the protein is monodispersed.
Just one question. So we have sort of accepted really mild detergents, C12, E8, and DDM. And exactly on those, this protein is unhappy. How do you explain that? You know, something horrible like OG, which is really quite aggressive, does very well.
So I don't know how to explain that.
I'm not sure about the estimate.
So, well, this assay basically what happens is that the protein is produced in DDM, and then is loaded to a column, and then the column is equilibrating a different detergent. Whether there has been complete detergent exchange or not, you don't know. You just run this profile, and what I can tell you is that the proteins that are crystallizing either in 3D and 2D, they all behave in this assay, in this particular assay, they all behave as a very sharp peak. They all display a sharp peak that is monodispersed. So once you have your protein and once you have access to homologs, the variables for 2D crystallization are relatively small. The crystallization space that we have been dealing with so far. Maybe there is a much bigger crystallization space that we don't know of, but the crystallization space is relatively small. We use relatively low protein concentration. We always use kind of the same lipids. Lipid to protein ratio very important. We use different detergents. There are no precipitants used usually on 2D crystallography, and the pH range and ion range is also relatively small.
Why DLPG?
Well, because many of these proteins are bacterial proteins, and of course the E. coli membrane is 80% PE, 20% PG, and we thought that adding a lipid, which is quite prominent in their biological medium, would help.
Did it work well?
For one of the proteins, I'll show you one example that I picked up actually one time. So to basically to do all this in one go with all these different homologs, we had to really set up crystallization on a 96 well format. This is the problem of doing many crystallizations in parallel has been addressed by many labs. Andreas has addressed it in many ways. Werner too, Gepard, Scherler too. So this is just one way of doing it. So what we did was to develop a 96 well crystallization block, which is basically, the block is designed on a 96 well format made of acrylic plastic. The sample wells are here at the bottom. Then we have a dialysis membrane, which is stacked in between two silicon sheets. And then we have the upper part of the block, which contains the dialysis buffer chamber. Here you have it in a bit more detail. We can put 50 microliters of sample, and then the sample is dialyzed against basically 20 times its volume in buffer. And with this approach, really is absolutely tight. There is no cross-contamination. We can put a dye in the sample in any of the sample wells, and it does not migrate to anywhere. And the block is $500 to make, and relatively easy to do. So we first tested whether the block, the dialysis block, will be able to dialyze not only detergents with high CNC, but detergents with low CNC too. So if you take a detergent with high CNC, like octaglucoside CNC of 20 millimolar, really dialyzes away very, very fast. And if you take something like DDM, of course, has a very low CNC, 0.12 millimolar, and it takes a long time to dialyze. But what happens is that with this block, you can really easily, very easily remove the dialysis buffer, exchange the dialysis buffer, and when you do in the order of about 10 exchanges, and you can perhaps do 3 or 4 exchanges on one day, really the detergent is dialyzed relatively fast.
How do you exchange it? By hand?
By hand. You can either use a robot, or you can use an 8-channel pipette, which almost any other lab has. And something else I forgot to say is that the idea of these chambers is that you can use 96 different buffers here. So you are not restricted to one single dialysis buffer as some other systems are. And because it's 96 well technology, and there is really a variety of vendors that are all the time developing things, we just bought this VarioShake thermomag, which basically takes the plate, has absolute temperature control, so now you can do temperature cycling, go above and below the phase transition temperature of the lipids, and it also shakes. So there's always 96 well technology is really developing very fast.
Iban?
Yes.
Maybe I understand not really well the experiment you show on the left side. If I have well understood, it's a dialysis setup, and you change the outer volume by preparing off.
Yes, so here in the left we haven't done anything. This is
And
just
on the right side, or DDM?
On the right here, this is buffer exchanges. Each of these points, we just took those that milliliter
So
of buffer.
my
and we replaced it.
question is, but maybe Tom has an explanation, but if it's dialysis, the molecule that goes through the dialysis bag is the monomer.
Yes.
Then the rate is governed by the gradient of monomer, which is in the case of DDM, if I remember well, 0.2 millimolar. So whatever the volume that you have outside, the rate is governed by this 0.2. So if you just change by that 20 times, you would not change the detergent concentration.
You are absolutely right. What drives dialysis is the chemical potential difference between the two sides of the membrane. And I don't know why it happens, but this happens all the time. Somehow there is some sort of removing perhaps some local concentration around the membrane of buffer with higher concentration of detergent. We don't really understand why.
Is the membrane acting like a biobead?
It's a dialysis.
How did you make your detergent concentration?
How did I measure? Oh, this with a chromogenic assay to measure sugars in detergent. It's very accurate. It's called the amino black assay, published by Tony Warren and the Passion. Anyways, these are just examples that we used at the beginning. We tried to crystallize well-known membrane proteins. We used LH2 because it was in a detergent with high CNC, or here we could get crystals that diffracted relatively fast, and we also used a copper transporter, one of the proteins in the lab of David Stokes, which was also it was solubilized in DDM to show that we could really also get crystals from proteins in DDM. So now that you have a 96 well block, if you want to look at it, each condition is one EM grid. So you need to inspect them by negative staining. So what you need is you need to be able to do staining again on a 96 well format. So what we do is we designed a platform shown here. This is a zoom of each of these filter columns, where we Here you have the dimensions. We then cover this with a brush with just grid glue from EMS, and we just apply the grids here, and then we can just use the robot. We apply sample to microliters of sample, and then we use the robot. We apply 5 microliters of a stain. We need to use very low stain concentrations, and the robot will apply the stain, and then we'll remove the stain, apply a stain, remove the stain, so there is no blotting involved. At the end, you will be left with a bit of a stain, stain solution, which will get dry, and if you do it at low enough stain concentrations, it does not give you any artifacts. This you can also do again with an 8-channel pipette. And we make the grids, we make the carbon-coated grids with continuous carbon using just nitrocellulose solubilized in amide.
How do you put the grids there, by hand?
Then you put them by hand. Once you are trained, 5 minutes.
Sorry, can you explain again the staining procedure?
So the staining procedure, you have the platform, you have the grids, and now you are either with a multi-channel pipette or the robot applies your specimen, 2 microliters. Then the robot goes, takes the 0.25% uranyl acetate solution and applies it on top. Then the robot comes and removes 7 microliters, goes back, applies another 5, removes 5, applies, removes 5, and after 3 times, leaves it there.
So you wash 3 times uranyl acetate, no water?
No water. Well, and then the other thing is that now you have 96 grids, and each grid has to go through the airlock into the microscope, and then you have to image, and this is really now no longer science, but closely to torture. You might be able to do it in Guantanamo, but certainly not somewhere else. So what we did, well, there were 2 options. One was the Gatling gun developed by Gatan. It's a special stage that can hold up to 100 grids and image them automatically. And we went that way, but we didn't follow through. And I can explain you later if you want to why. The other option is basically something similar to what Bridget Carragher has been using at Scripps. So we went through that route, and basically we contacted a company, JDK, that develops crystal mounting robots for synchrotrons. So they really know how to deal with crystals and how to mount them into any instrument. So this is basically a schematics of a microscope. The robot is sitting on a table. This in black is a Cartesian robot. It can only move in the X and Y plane, shown here if you look at it from above. And then there is a SCARA robot. This is a pivotal, three pivotal points robot. The robot has a suction device. The robot goes and picks up the grid by suction from the platform. It has a laser. It knows whether the grid has been loaded or not. And then this robot, this pivotal SCARA robot transfers the grid to this other black robot, the Cartesian robot, which holds a stage, and then this robot goes and inserts the stage into the microscope. And so the transfer device and grid imaging is all controlled by Leginon. So Bridget Carragher has been helping us to optimize Leginon to first work on a low-end 1230 GOL microscope, and then to also serve as a management software for the robot as well. And the robot can, of course, using Leginon, you can make a montage of low magnification pictures, and you can then look at those pictures, select them, and then tell the robot to go back to load certain grid and to image a section and take high magnification images of that section. In this way, about 100 grids, one entire block, can be imaged per day. So the robot has not been yet installed, has been designed, supposed to be installed in September. So, and once it's completely developed, it will be available for purchase by other labs. At the moment, it's a bit expensive. So this is a screen with one protein. We've screened about 10 proteins so far. Proteins that all purify well, express well, and behave very well in detergents. This is just an ICOMS code. It doesn't mean anything. This is a zinc transporter, which shows very nice gel filtration profile in DDM. So what we do is we set up the block, and we cover, as shown here, several lipid classes with several LPRs, and we are covering either salt concentration or pH space. So the first thing is that once you look at those images, you need to now qualify them somehow. So as you can see here, if you go to DMPC, LPR of 0.1, you have many of the so you have this entire row. Here is the color code of that row, and this is here is the definition. And A in blue means that you have actual crystal lattice. You've been able to record an image and to calculate a Fourier transform of it and be able to observe a calculated diffraction pattern. B is when you have tubular vesicle sheets and physical grow, but they don't diffract. C, vesicle clusters. D, when you have protein aggregates. And E is when you have just lipid streams or very strange shapes.
So this you check, the user checks this?
Yes. So later on, when Legionnaire is completely working, we should be able to use object recognition methods to do some of this. But at the moment, the
you
user
decide what you see.
the user does it. And here the object prevalence is 1, 2, 3, and 4. 1 is when you see less than 10 objects, 10 to 20, 20 to 30, 30 to 40, and so on. And when you don't see anything, this means that you really either your grid was broken, your carbon was broken on the grid, or the staining was bad, and this happens very seldom. But most of the times what happens is that your protein, your sample has aggregated in a way which does not transfer well to the EM grid. So what we do is, before we apply all these samples to the grid, we look at them on the light microscope. We just take a microscope slide, we put, let's say, this entire row of conditions, and then we look at it on the light microscopy, and if we see large aggregates by light microscopy, those aggregates in our hands never transfer to the EM grid. So there's
how can you exclude not nice crystals there? Because sometimes beautiful crystals cohabitate with aggregates.
So that could be. But so often we still transfer them to EM grids and we don't see anything.
You often find crystals growing out of aggregates.
Yeah. This is what we call physical growth. So in those cases we do see material on the EM grid. So in this case, for example, this protein showed, in this case, these are helical crystals on DOPG. If we now change the pH, exactly the same conditions, the same protein concentrations, it's only the pH that has changed. We see that now we are getting many crystalline objects on the grid, but most of them concentrate to DOPG, very, very little in DMPC. And so in this case, if we had not done this screening at pH 7, we would have been missing good crystals, and if we had not included DOPG, we would also be missing crystals. So basically the idea is that in this way, it allows you to really cover much more crystallization space. I just chose these lipids, but you might choose different ones. If you start looking at what are the most common lipids in which membrane proteins crystallize into D, of course DMPC and some colloid lipids and DOPC are always there, but there might be other lipid combinations that might be better. And in this way you can really check them without finding it a daunting problem. So this is this sample, one of the conditions at LPR1, pH 7, this is a zinc transporter, so we have to use zinc. So we don't do this blindly. It's not that we do, we know what these proteins are. Most of the times let's say we identify about 10, 15 proteins that we are interested in. NICOMS finds homologs of those proteins and then expresses them and purifies them for us. So we know whether the protein is a zinc transporter, like in this case, where we obtain tubular crystals that look very nice. They're negative stain. So the staining is quite good, as you can see, and this was all done with the robot. And I'm not showing the best image. Really, it took us 1 month to get this working. And this is, you take cryo images of these crystals, and indeed they show third order diffraction, chemical diffraction. We also have 2D crystals. This is now intramembrane protease, which really likes DMPC. It does not like DDM, completely precipitates in DDM, so you need to use phosphocoline 12. And very similar LPR, in this case a pH 6, and we can get now 2 tubular crystals of this protein. So we've been working at this for 1 year. We just now basically, so far we've been doing the imaging, all that manually. We hope that the robot should be completely operational in the next couple of months. And the task for the next 2 years is to screen about 100 membrane proteins, to do about 2 times 96 to search 2 times 96 conditions initially for those proteins, and then identify the proteins that really crystallize or that show tendency for crystallization, and to redo this process, and then start the structural determination using OSBC facilities. We are also applying this to EMRE, because I still think that crystals, EMRE crystals can be improved, and there is no reason why they shouldn't be improved. So not only we are starting from zero, but also with some membrane proteins that have diffracted to medium resolution. We are only working on EMRE. We haven't started to work on any membrane protein with anybody else.
Not yet.
And at the NYSBC, we are well suited to do all this kind of work. I am affiliated to Mount Sinai. NYSBC is just a facility of Mount Sinai and the other 9 institutions of New York. I'm not affiliated to NYSBC, but I use their facilities. So the robot will be mounted on the 1230. We also have an F20, a 2100, and a 3200 in case we obtain very good high diffractive crystals. And Ruben Diaz is present here. There at the back, he's the technical manager of the entire facility, so you can talk to him if you want more information. So I'd like to thank people involved in this project. David Stokes and I lead this project and wrote the grant that got funded to do this project. And we share 2 postdocs and a technician. The technician makes the membrane proteins, and the 2 postdocs do the imaging and analysis. And we couldn't do this without the help of NICOMS, headed by Wayne Hendrickson. The 2 people that developed the robot are John Coase and Kevin Davico from the JKD Instruments. And Martin Bink at the YSBC was also very helpful, and Katie there and Ruben Diaz as well. And Bridget has been helping us with the optimization of legionnaires. Thank you very much for it.